This is section 10.2, vectors in space. These are the objectives. You can pause to read. I am moving on to the next slide. You're going to notice that the concepts and the formulas that you're going to see on this section look familiar because you have done this lesson on a plane. Now we're going to be looking at vectors in space. So here we go. Here's the dot product, and there's the formula. Parallel vectors, the same applies as you saw in a plane. And it says where c is a scalar. Remember, this is just a constant. Then the magnitude of the vector, the formula looks familiar. Perpendicular vectors, the dot product is equal to 0. Then they are perpendicular, or they are form a 90-degree angle between them. The unit vector is the vector divided by the magnitude of the vector, and component form of a vector is the terminal point minus the initial point. Next slide. It says write several parts here. Write the part A is component form of a vector, part B find the magnitude of the vector, and part C is find the unit vector in the direction of V. So the initial point is given, the terminal point. So let's find the component form, which is part A of the problem. So terminal point minus the initial point components. Simplify, you end up with this. So we're done with part A. Now we're going to find the magnitude. So all we need to do is take these numbers that you see here, square them, and take the square root. We follow the formula you saw on the previous slide, and you end up with square root of 67. Letter C says find the unit vector in the direction of V. So we apply the formula you saw on the previous slide, which is 1 over the magnitude of the vector times the vector V, and which is right here, and this is the answer. You can leave it in this form. We're done with number 1. Let's go to number 2. It says find a unit vector, part A in the direction of U, part B in the direction opposite to U. So basically we're going to focus on this part. But first we need to find the magnitude of U. And once we do that, we take these numbers, -3, 5, and 10. We apply the formula, and you end up with radical 134. And then just bring over vector U, and this is the answer to part A. Part B, what we're going to do is take part A and multiply by -1, and that's how we find a unit vector in opposite direction of U. And that's why you see this as your answer. Notice that I distribute the negative into each of these terms here inside the parentheses. And we are done with number 2. There's applications to part B. That's why you need to be familiar with this. It may seem kind of silly to do part B, but like I said, there's applications to this coming up soon. Next slide. Says find the dot product of U and V, so we apply the formula. So here's vector U. Notice that this is missing the I component, so that's why we can rewrite it in component form as 0, 3, -6, and then I'm going to multiply this times the components of vector U, and once I do that, this is the operation that I must follow, and it turns out to be 0. So the dot product of U and V is 0. Let's move on to number 4. It says find the angle theta between the vectors. So I'm going to use the formula you saw on the second slide. And this is the formula. Cosine of theta is equal to U times V over the magnitude of U times the magnitude of V. If you take the dot product of U and V, you end up with 5. If you take the magnitude of this, you end up with radical 10. Take the magnitude of this, you end up with radical 6. I didn't show you this, but I mean, I'm sure you can come up with this very easily. And if you want me to, I can clarify this in class. But like I said, it should be pretty easy. And then at this point, all I need to do is I need to find the theta. So then I do theta equals cosine inverse of this expression that you see here, and you end up with 65.47 degrees. So make sure the mode is in degrees. Let's go to the next slide. It says determine whether U and V are orthogonal, parallel, or neither. Remember, this means perpendicular. So here we go. This is what we're going to use. First, we're always going to check for parallel, and then if they're not parallel, check for perpendicular, and if they're not perpendicular, we know they are neither. So let's check for parallel, and there's no way, there's no C that once I multiply times vector V, I get U. So that's why these two vectors are not parallel. So now let's check for perpendicular. So I'm going to take the dot product, and it turns out to be 0, which means that vector U and vector V are perpendicular, orthogonal. Let's go to number 6. So we're looking at vector U, vector V. I'm going to check to see if they're parallel. See if there's a scalar that I can multiply one by the other so I can get the other vector. And it turns out that there is. If you multiply vector V by -1/8, you end up with vector U, which implies that these two vectors are parallel. Let's move on to number 7. Here we go. This is going to be a little bit challenging, but not as much as number 8, which is the last problem. So here we go. The vertices are given. Determine whether the triangle is an acute triangle, an obtuse triangle, or a right triangle. And you have the 3 points. You can actually graph these points and connect them, and you'll be able to see this a little bit better. But I'm not going to. I'm just basically going to use the points here. So first thing I'm going to do, again, I'm going to refresh my memory. If the product is equal to 0, I know they are orthogonal. I can come up with this. If the product is equal to greater than 0, I know that the vectors are the vectors form an acute angle between them, and also if the product is less than 0, the vectors form an obtuse angle between them. And if you want me to clarify where I get this, I'm using an extension of a formula you saw on an earlier slide in this video. Talk to me in class and I'll clarify it even more. So here we go. So I'm going to call vector U the following vector, terminal point P minus initial point Q. So I take these points minus, this point minus this point, and this is my component form, which I'm calling vector U. Then I'm basically going to find another vector, and I'm going to start with the same initial point, Q. Notice that they match, and I always want my initial point to match. And my terminal point is going to be, of course, different than vector U. So now I'm using terminal point R. And once I apply the subtract the values in the points, I end up with this vector and component form 1, 2, 3. Then I do take the dot product, and I'm going to check to see what happens. Once I take the dot product, I end up with -3, which means that I'm over here. Since the vector is, the product is less than 0, is -3, I know that the angle between them is an obtuse angle, thus making this an obtuse triangle. Let's go to the next, the last problem of this video. Here's the last problem, number 8. Same directions as number 7. This problem is going to be a little more challenging than 7, but nothing that you can't handle. So we start out by summary of the angle formed by the two vectors. Let's find vector U. Vector U is going to be given by terminal point Q and initial point R, and I end up with this component form: -3, -3, 11. vector v, and notice that I have the same initial point, different terminal point for vector v, and this is what I get once I simplify. And I now take the dot product of these two vectors, and I end up with a positive number, so that's why I know that I'm actually over here. So I know that the angle between these two vectors is acute. Is it enough for me to determine that this is an acute triangle? No. It could be obtuse, it could also be a right. So I have to continue. Next, then I have vector W. Vector W is generated by the initial point Q and terminal point P. And then at this point, once I simplify, this is what I get for the component form. Then I'm going to have to come up with the same initial point, different terminal point, which is, again, same initial point, different terminal point. But notice that this is the opposite of U. That's why I have U sub 1. This is the opposite. All you need to do is multiply this by -1, and that's why I have this. So then I'm going to take the dot product of W and U sub 1. I also get a positive number, which means that the angle between these two vectors is also acute. Is it enough for me to conclude that this is an acute triangle? Not necessarily. It can still be a right triangle. It can also still be an obtuse triangle. So I have to do this one more time. So then I have vector V sub 1, because notice it's the opposite of V. So all I need to do is take this and multiply by -1. And then, and again, notice that the initial points match. W sub 1, which is basically the opposite of W. Take this, multiply by -1. Then I take the dot product of these two. I end up with a negative answer, which implies that the angle between these two vectors is obtuse. Thus, since it's obtuse, it makes a triangle an obtuse triangle. And I can clarify this a little bit more if you like. Just talk to me in class. But this concludes the video.